Hello, I'm Ed Murphy with the Astronomy Department at the University of Virginia, and this is Astronomy 1210 Introduction to the Sky and Solar System, Lecture 34, Jupiter. In this lecture, we're going to look at the largest planet in our solar system, Jupiter, and I'll give you just a quick tour of some of the main features of Jupiter. So let's start, as we have with the other planets, with some basic facts about Jupiter. Jupiter orbits the Sun about 5 times further from the Sun than the Earth is, at a distance of 5.2 astronomical units. Its orbital period is just a little bit less than 12 years, which means Jupiter covers one of the zodiacal constellations about every year. Since there are 12 zodiacal constellations, and with an orbital period of almost 12 years, Jupiter passes through one zodiacal constellation each year. Its orbit is tilted just a little bit with respect to the Earth's orbit around the Sun, just 1.3 degrees, and it has a fairly circular orbit. Its eccentricity is 0.048. Its diameter is 11.2 times the diameter of the Earth, which means its volume is more than 1,000 times the volume of the Earth. But its mass is only 317 times the mass of the Earth, which means that Jupiter is much less dense than the Earth is. Its average density is about 1.3 grams per cubic centimeter, whereas the density of the Earth, you'll recall, is 5.5 grams per cubic centimeter. All the terrestrial planets had densities over 3 grams per cubic centimeter. Most of them had densities over 5 grams per cubic centimeter. And this indicates that Jupiter, of course, is a gas giant planet, since it is just barely more dense than water, which has a density of 1 gram per cubic centimeter. And lastly, Jupiter rotates very quickly, 9.9 hours. That doesn't put it in perspective because given Jupiter's large size, Jupiter rotates in less than half the time it takes the Earth to spin on its axis, and yet Jupiter is 11 times the diameter of the Earth. So that puts it in perspective that the outer atmosphere of Jupiter is moving quite rapidly as the planet spins. Now, this is a fantastic ground-based image of what Jupiter looks like. So through a good telescope, you can easily make out a couple different features on Jupiter. You can make out these dark belts on Jupiter. So typically through a ground-based telescope, you will see 2 dark belts on Jupiter. On a really good night, you might make out more dark belts than that. You can see the great red spot on Jupiter. We'll see later on in this lecture that that's actually a giant low-pressure system. Giant high-pressure system, a giant storm on Jupiter. Occasionally, through ground-based telescopes, looking with your eye through the telescope, you can see other storms and white spots on the planet. Here's an image taken by the Hubble Space Telescope, which shows everything in greater detail. So now we see the north equatorial belt and the south equatorial belt, and the south equatorial belt has the great red spot right at its edge right there. There are other temperate belts. The white bands, as we'll see later on, are called zones, and then the darker bands are called belts on the planet. Now, Jupiter is a gas giant planet. It's made primarily of hydrogen. It's made about 78% molecular hydrogen. It's about 19% helium. Water makes up a tiny fraction of a percent, probably about 0.0001%. Methane is about 0.2%. Ammonia is about 0.5%. And Jupiter is interesting in that it gives off more heat than it gets from the Sun, 1.7 times as much heat as it gets from the Sun. And this internal heat inside Jupiter is heat that is left over from Jupiter when Jupiter formed. And it is that heat that drives much of the details that we can see. It is that heat and also the rapid rotation of Jupiter that drives a lot of the details that we see in the cloud bands of the planet. All right. So let's talk about some of the missions to Jupiter and to the outer planets. By far, the most important major missions to the outer planets were the 2 Voyager spacecraft. So Voyager 1 and Voyager 2 were launched in 1977 to take advantage of a rare lineup of the outer planets. With a single spacecraft, you could visit Jupiter, Saturn, Uranus, and Neptune. So it was decided that Voyager 1 would visit Jupiter and Saturn, but because scientists wanted to get a close-up look at Saturn's moon Titan, it was decided that Voyager 1 would take a close look at Titan, but the gravity from Titan would then fling Voyager 1 out of the solar system. Once they had a good look at Titan with Voyager 1, that freed up Voyager 2 to avoid Titan and go on to visit Uranus and Neptune. So Voyager 2 visited Jupiter, Saturn, Uranus, and Neptune, and it used the gravity of one planet as a slingshot to fling it on to the next planet. So here is the position of Jupiter in 1979 when it was visited by Voyager 1 and Voyager 2, and then Saturn. Voyager 1 was flung out of the solar system after visiting Saturn in 1980. Voyager 2 was then flung onto Uranus, and from there onto Neptune. That was the Voyager 1 and Voyager 2 missions. Jupiter and Saturn had been visited previously by Pioneers 10 and 11, so Voyager 1 and Voyager 2 were not the first spacecraft to visit Jupiter and Saturn. However, Voyager 2 was the first and is still the only spacecraft to have ever visited Uranus and Neptune. Since 1986 and 1989, respectively, we've not visited Uranus and Neptune. There are some hints that NASA might like to go back and send spacecraft to Uranus and Neptune, but it's not clear that those missions will happen, probably not until the 2030s at the earliest. Well, after the missions to Jupiter and Saturn by Voyager 1 and 2, enough new information was turned up that dedicated missions were called for. And so, after Voyager, NASA and the European Space Agency developed the Galileo mission. The Galileo mission was launched to Jupiter in October of 1989, and it studied the planets and its moons from December of 1995 to September of 2003. The Galileo mission included a probe that parachuted down through the atmosphere of Jupiter, taking data. We'll talk a little bit about that in a few minutes. There was one unfortunate incident with the Galileo mission, which was that it had on board a very large high-gain antenna. This high-gain antenna was going to be used to transmit all the data that the spacecraft gathered at Jupiter and send that data back to Earth. Unfortunately, in order to get Galileo out to Jupiter, there was no rocket large enough in the U.S. Inventory of rockets to go directly to Jupiter. So instead, Galileo was sent to the inner solar system, where it had a flyby of Venus and then was projected from there to the outer solar system, all the way out to Jupiter. While it was in the inner solar system, they wanted to keep the high-gain antenna furled up, so it was left furled up. It wasn't deployed because they didn't need it when it was in the inner solar system. As Galileo headed to the outer solar system, when they tried to deploy the antenna, they discovered that some of the pins holding it in place were stuck, and they were never able to deploy this high-gain antenna, which meant that Galileo was not able to send back to Earth nearly as much data as had originally been hoped. Now, this wasn't the only antenna on board. There was a small low-gain antenna, which means it can't send very much data, but it was that small low-gain antenna that was used to send the data back to Earth. So the main high-gain antenna didn't deploy as planned, and so that limited the amount of data that could be returned to Earth. The same was true for Saturn, as we will see when we talk about Saturn. There was the Cassini mission to Saturn was a dedicated mission to Saturn, unlike the Voyager missions, which were flybys, where you literally just fly by the planets and take pictures over the course of a few hours or a few days as you fly by. Both the Galileo and Cassini missions were orbiting missions that would spend many years in orbit around the planets. And so the Cassini mission was launched in October of 1997 and arrived at Saturn to study Saturn and its moons in 2004. And we'll learn more about the Cassini mission in the next lecture on Saturn. So what is inside Jupiter? Well, Jupiter's a complex planet. First of all, it's a gas giant planet, so it has probably no solid surface underneath. If we were to start at the top of Jupiter's atmosphere and work our way down, the first thing you'll remember is that Jupiter is made primarily of hydrogen with a little bit of helium. And if we start at the upper atmosphere and work our way down, initially we would encounter a gaseous hydrogen atmosphere. So this is just hydrogen gas. As we get deeper inside Jupiter, when we get, it looks to be about 10% of the way down inside Jupiter, we reach a layer where the hydrogen atoms are so dense and packed so close together that they take on the characteristics of a liquid, and we call this a liquid hydrogen envelope. As we continue deeper down inside the planet, down here where the density gets up to about the density of water, 1 gram per cubic centimeter, the hydrogen transitions over to becoming a metal. And we have this large region inside Jupiter where the hydrogen atoms are acting like metal, and we call that the metallic hydrogen region of Jupiter. Now, you might wonder, why does hydrogen act like a metal? But think about the periodic table of elements. Hydrogen is found over here in the first column of the periodic table. And lithium, sodium, potassium, rubidium, cesium, francium, those are all metals in that table, in that column of the table. And hydrogen, being in the same column, behaves the same way that they do. The difference is that hydrogen is a gas. All of these are solids at room temperature. So when hydrogen is a gas, it's a little bit hard to see its metallic properties. But now that we cram it together at very high densities inside Jupiter, those metallic properties come out. But as you can imagine, if you think back to the Earth, now we have a large metallic core inside Jupiter, not made of metals, but made of metallic hydrogen. Metallic hydrogen is an excellent conductor of electricity. There is also convection going here, hot hydrogen rising, cool hydrogen sinking down, and Jupiter is spinning very rapidly. And as you can guess, those 3 things, a conducting core, convection in the core, and rapid rotation, results in a very strong magnetic field around Jupiter. And then deep down in the center of Jupiter, it was believed that we would find the rocky, icy metal core of Jupiter. You'll remember in the model of the formation of the solar system, Jupiter, Saturn, Uranus, and Neptune, they all start with rocky, icy, metallic cores. And these rocky, icy, metallic cores build up very large, very quickly, and then their gravity is strong enough that they can pull hydrogen and helium gas in. And as they pull that hydrogen and helium gas in, eventually the hydrogen and helium gas come to dominate the mass of the planet. But down there at the center of Jupiter should still be that original core. Now here's the thing. It's not going to be a solid core like you may imagine it. Look at the numbers here. The core of Jupiter is 20,000 Kelvin. It's probably hotter at the center, maybe even up to 30,000 degrees Kelvin at the center. That's 5 times hotter than the surface of the sun. And the density down here is an amazing 25 grams per cubic centimeter. That's denser than anything that we find on the Earth. And what's interesting about this metallic hydrogen is when it gets down here, it's much, much denser than water, but it still is a gas. It's just the atoms are very, very closely packed together. So that is the interior structure of Jupiter. We'll see here in a minute how the Juno spacecraft has modified our knowledge of what's going on deep down inside Jupiter. So right now in orbit around Jupiter, NASA is operating the Juno spacecraft. So Juno is the second dedicated mission to Jupiter after the Galileo program. And the whole goal for the Juno spacecraft is to teach us about what's going on deep down inside of Jupiter itself. So the Juno mission is orbiting Jupiter on a very elliptical orbit that takes it close over the 2 poles of Jupiter, over the north and south poles of Jupiter, and it gets very, very close to the atmosphere, very, very close to the surface of Jupiter as it orbits around Jupiter. So its goals were to measure Jupiter's composition, measure the gravity field of Jupiter, because the gravity field can tell us in detail about what's going on deep down inside Jupiter. Its magnetic field, which is generated in that metallic hydrogen core of Jupiter, or that metallic hydrogen layer, I should say, deep down inside Jupiter. So that magnetic field can tell us about that layer. The polar magnetosphere, which is the outer regions of Jupiter's magnetic field outside the surface where it interacts with the solar wind. And we had probed the magnetosphere before with the Voyager and the Galileo spacecraft, but now the Juno would be orbiting the poles of Jupiter. We can learn more about what's going up there with the magnetic field near the north and south poles on Jupiter. And again, from the gravity field, we can get the mass distribution inside of Jupiter and learn about that core that might be down there, learn about the winds that are going on below the surface. And then finally, a really important thing about the composition of Jupiter is knowing how much water it has. So just a couple images from Juno. So here's one of the more spectacular images, I think, from Juno. Juno carries a camera on board called JunoCam. And JunoCam was specifically designed for public outreach images, but lots of them have been very, very scientifically valuable. This one, I argue, is a little bit more towards the aesthetic public outreach value. It's an eclipse on Jupiter that is the shadow of Jupiter's moon Io as seen on the cloud tops at Jupiter. But other things that JunoCam has shown us is up at the north and south poles of Jupiter, there are polar vortices, these polar vortices that are about the size of our planet, not quite the size of our planet, each one, but orbiting around the poles up there at Jupiter. And I would argue one of the more interesting results that has come out of Juno so far is that Jupiter does not have down at the bottom a very dense core. So we thought that from the formation of the solar system, Jupiter should have this icy, rocky core to it. But what we're finding from the Juno mission instead is that core is much more dilute, that core is not concentrated down at the center of Jupiter, but it is spread out over a much greater distance. Now, either this is just simply due to the interior structure of Jupiter, or one proposal that has been put forward is that early in the solar system, a very large body, a Uranus or Neptune-sized body, collided with Jupiter, and that collision took this material in the dense core, stirred it up, and as it stirred it up, it expanded or it extended that material through a much more dilute core. So what we have inside Jupiter today is that dilute core and an enriched envelope here that has more of those heavy elements in it than we had expected. But in any case, that is the current model for the core of Jupiter. It does not appear to have a solid, dense core, and that means that you probably could start on a parachute at the top of Jupiter and parachute all the way down to the core and never reach a solid surface. The interiors of the other Jovian planets are probably the same. We don't know anything or don't know much about them because we haven't had missions that have orbited as close to the cloud tops as the Juno mission has orbited to the cloud tops of Jupiter. And that means that we don't know their interior structure nearly as well. What we do know is that Uranus and Neptune are not large enough to have the giant liquid hydrogen and metallic hydrogen cores. And so they probably just have a gaseous hydrogen envelope, some kind of water and methane and ammonia envelope, and then surrounding that, possibly the liquid hydrogen, but not the metallic hydrogen core. Now, an interesting fact about Jupiter and Saturn is that Jupiter is more than 3 times more massive than Saturn, and yet the two planets are the same size. And you might wonder why it is that Jupiter has 3 times the mass of Saturn, but is only slightly bigger. And the answer to that is compression. So imagine taking a stack of pillows. As you add more and more pillows to the top, the weight of the overlying pillows compress the underlying pillows. And this compression means that as you add more pillows to the stack of pillows, if you add twice as many pillows, the stack doesn't get twice as tall because the weight of those additional pillows compress the ones underneath. The same is true with the planets. As we add more and more mass to the planets, they do not get significantly bigger, and that's because they compress the gas in the lower layers deep down underneath the surface. Now, I mentioned that Jupiter is rapidly rotating, as is Saturn. And this rapid rotation means that these planets are not perfectly spherical. They're not round. As they rotate very, very quickly, the equators bulge out and the poles are a little bit narrowed down compared to a perfect sphere. So the rapid rotation of the Jovian planets results in a non-spherical shape. And in the case of Saturn, which has probably the most non-spherical shape of all the planets, that's actually easily noticeable in a small telescope. When you look at Saturn through a telescope and you imagine what a perfect circle looks like, you will see that Saturn is significantly shorter around the poles than it is around the equator. Measurements of Jupiter indicate that it too is wider around the equator and narrower around the poles. It's just not as obvious when you see Jupiter through a telescope. And of course, images taken by the Galileo spacecraft and by JunoCam show that Jupiter has a tremendously complex atmosphere. an atmosphere that is dominated by large storms, by belts and zones. We'll talk about what those are in a minute and the interactions between those belts and zones. The color of Jupiter's atmosphere is a really interesting puzzle to this day. The reds and the browns, it's not exactly clear where they come from or what the chemical reactions are that drive those red and brown colors in Jupiter's atmosphere. But based on the composition of Jupiter, we can make some reasonable guesses about what the atmosphere of Jupiter might be like. And as we go down towards the center of Jupiter, it gets hotter and hotter. As we go higher and higher in Jupiter's atmosphere, it gets colder and colder. So we can imagine that convection, hot material, will rise up. And eventually, as that hotter material rises up, it will condense. And different material will condense at different temperatures. So here's a plot of the cloud temperatures on Jupiter. And we can see that here's the temperature, 100 Kelvin, 200 Kelvin, 300 Kelvin. As we go deeper and deeper inside Jupiter, it gets hotter and hotter. There is an inversion here where once we reach this cold temperature, as we go higher and higher in Jupiter's atmosphere, it also gets slightly hotter. But what happens is the interior material, as it rises up, will condense at various layers. And we believe that there should be 3 cloud layers inside Jupiter. The lowest of those cloud layers is a water cloud layer, just like on Earth. As this hot, moist material rises up, eventually, once it gets below a temperature of the condensing of the boiling point of water, once we get below 100 degrees, once we get below 200 degrees Fahrenheit, water will start condensing to form clouds. And as water starts condensing, we will get a layer of water clouds there. Above that, we'll have a layer of ammonia hydrosulfide clouds, and then above that, we will have a layer of ammonia clouds. Now, the ammonia clouds and the water clouds are expected to be white in color, and it is the ammonia hydrosulfide clouds that give us the brown and red colors in the atmosphere of Jupiter. So, here's what the atmosphere, here's another plot that shows us pretty much the same thing for Jupiter, but it also shows us the other planets in the solar system, Saturn, other gas giants, Saturn, Uranus, and Neptune. So here are the ammonia clouds, deeper down the ammonium hydrosulfide, below those the water clouds. Saturn should have the same 3 sets of clouds, but because Saturn is cooler than Jupiter and it's not releasing as much heat, those layers occur much deeper in the atmosphere. So you will notice that if we have this particular layer, we're just going to call this altitude on these planets 0. The clouds on Jupiter are much closer to that altitude than they are on Saturn. On Saturn, those cloud tops are buried much deeper in the planet, which explains why Saturn, although it has the same cloud layers as Jupiter, those cloud layers are harder to see and they're much more subtle because they're buried much, much deeper. Uranus and Neptune, on the other hand, have significant methane clouds in them, and that gives them that bluish blue-green color that we see with Uranus and Neptune. Now, one of the most prominent features on Jupiter are the zones and the belts. So when we look at Jupiter, we see these brighter colored zones separated by darker colored belts. And on Jupiter, we see zones and belts and zones and belts going all the way up to the polar regions. The zones are regions where hot material from underneath is rising up. And the belts are where cooler material is sinking down. And so if we look at Jupiter, we see the zones, which are the brighter colored regions, and the darker colored belts right here. And so the zones are the higher material. And what we're looking at here, that bright material we're looking at, are ammonia clouds. These are ammonia clouds in the high cloud tops. In fact, it probably gets so cold there that ammonia snow falls out of these high clouds down into the deeper layers where the snow evaporates and then rises up with the next upwelling of hot material, condenses ammonia clouds, snows out again, and falls down. The zones are higher up and colder than the belts. When we're looking at the belts on Jupiter, we're actually looking deeper down in the atmosphere. And you can see that here. You can see that the zones are higher up than the belts. Another way to tell that is with an infrared image of Jupiter. Now, infrared light is a measure of the temperature of the clouds on Jupiter. And we can see that the belt regions here are brighter in the infrared, which means they're warmer. and the zones, which are higher up, are cooler. So when you are looking at Jupiter and you see the zones and the belts, you're looking at different layers in Jupiter's atmosphere. With the zones, you're looking at the upper layer, and with the belts there, you're looking deeper down in the atmosphere. And in addition to the very rapid rotation of Jupiter, this is an image that a movie, I should say, of the movement of the clouds on Jupiter that was taken by the Cassini mission. As Cassini flew by Jupiter on its way out to Saturn, it used Jupiter as a gravity assist to get on out to Saturn. And we can see the rapid rotation of the great red spot here. And we can also see the motion, the wind motion of the zones and the belts right there, and the interaction of the two. Now, with the Galileo mission, not only did Galileo put a probe in orbit around Jupiter, but Galileo also had a probe that parachuted down through the outer atmosphere of Jupiter. The Galileo probe slammed into the Jupiter's atmosphere, traveling 106,000 miles per hour, and transmitted data for 58 minutes, while it descended through about 200 kilometers of Jupiter's atmosphere. Now, this sounds like a lot. It sounds like 200 kilometers of Jupiter's atmosphere is quite great. But remember the tremendous radius of Jupiter. This would really just barely scratched the surface of Jupiter's atmosphere. However, the region that it parachuted down through was this really important region on Jupiter where we expected to find the clouds. Ultimately, what caused the demise of this probe was as the probe sank deeper and deeper inside Jupiter, the pressure got higher and higher, and eventually 200 kilometers below the upper layer that it first started probing, the pressure got so great that it crushed the probe and it stopped transmitting back to Earth. But that was the Galileo probe. So we have, in fact, parachuted down through the atmosphere on Jupiter, measuring the various layers deep down inside Jupiter's atmosphere. Okay. In addition to Jupiter's atmosphere, Jupiter has the Great Red Spot. So the Great Red Spot is about twice the size of our whole planet. So we could take one Earth and put it here. We could take another Earth and put it right there. The Great Red Spot is easily visible even in a small telescope from Earth. Now, the Great Red Spot is interesting because it changes its appearance over many decades. Sometimes it appears much redder. The last decade or so, it has appeared much paler. But it does change its appearance, and it changes how deep red the Great Red Spot is. So sometimes it's much redder and much more noticeable than other times. What the Great Red Spot is, we can tell from its rotation, is that it is a high-pressure system. So in the southern hemisphere, high-pressure systems turn counterclockwise and low-pressure systems turn clockwise, whereas in the northern hemisphere, it's exactly the opposite. Low-pressure systems turn counterclockwise and high-pressure systems turn clockwise. And the reason for this rotation around high and low pressure systems on Earth and on Jupiter is an effect called the Coriolis effect. So the Coriolis effect comes from the fact that the equatorial regions are moving faster than the regions at higher latitudes. So as gas moves from one region to the other, it not only moves north, but it pulls ahead of the material at more northern latitudes because it was moving faster as it moved around the equator. So let's take a closer look at this thing called the Coriolis effect. So on Earth, the Coriolis effect causes high and low pressure systems to rotate. So let's look at what's going on with the rotation of the Earth. Here on the equator of the Earth, somebody spinning around the equator of the Earth makes a full circle in 24 hours. Somebody up here at the northern latitudes also makes a full circle in 24 hours. The difference is this person travels a much smaller distance than this person does down here. Because this person travels a much greater distance, they're moving much faster. So imagine that you traveled from the equator towards the north. Imagine, for example, that we shot you out of a cannon and you were moving towards the north. Here on the equator, you're moving at about 1,600 kilometers an hour. But up here, you're only moving about 1,200 kilometers an hour, which means as you move to the north, you are also going to travel to the east because you had started your travel with a sideways velocity of 1,600 kilometers per hour. And as you get further north, this land, this surface of the Earth, is not moving that fast, and so you pull out ahead of it. And so what happens on Earth with a low pressure system here in the northern hemisphere? Let's imagine a low pressure system. A low pressure system is pulling gas into it. As gas gets pulled into that low pressure system from the south, this gas is moving too fast, and so it ends up curving off to the east. On the other hand, gas from the north that gets pulled into the low pressure system, well, the low pressure system is moving faster than that gas is, so that gas gets left behind. As this gas gets left behind, as this gas goes forward, it sets up a counterclockwise rotation around that low pressure system. Now, hurricanes on Earth are low pressure systems, and that is why hurricanes on Earth always spin, in the northern hemisphere, I should say, always spin counterclockwise. In the southern hemisphere, the opposite is true. In a low pressure system, this gas gets pulled out to the front, this gas gets left behind, and so in the southern hemisphere, low pressure systems always spin clockwise, but they always spin counterclockwise in the northern hemisphere. So here in the northern hemisphere, low pressure systems spin counterclockwise, low pressure systems in the southern hemisphere spin clockwise. High pressure systems spin counterclockwise in the southern hemisphere, and high pressure systems in the northern hemisphere spin clockwise. So from the spin of the Great Red Spot, so if we go back to our movie here a second ago, you can see that the Great Red Spot is spinning counterclockwise. It is in the southern hemisphere, and since it is spinning counterclockwise in the southern hemisphere, it must be a high pressure system. Now, what's amazing about the Great Red Spot is it has been visible in telescopes for well over 200 years, probably going on 300 years now. It has been visible in telescopes, and it has been present on Jupiter that whole time. We don't know whether the Great Red Spot is a permanent feature on Jupiter or whether it is a storm that just happens to be particularly long-lived. We just know that it has been around since we have had telescopes to look at Jupiter. The Great Red Spot has been there. All right. And then there are these bands, the zones and the belts on Jupiter, and the interactions of those zones and belts. Convection on Jupiter is what drives the winds in these zones and belts. And these winds penetrate deep down inside Jupiter as well. And so we have a large equatorial region, and then we have other, you can think of them as cylinders deep down inside of Jupiter that are spinning rapidly. Jupiter has a very strong magnetic field, and we saw that earlier that strong magnetic field comes from that metallic hydrogen core that also has convection going on, where the hot gas is rising, the colder gas is sinking down, and the rapid rotation from Jupiter. Initially, it was believed that Jupiter has a field like the Earth, a dipole field with a north and a south pole, and that field was tilted over. But recent observations by the Juno spacecraft indicate that Jupiter has, in fact, a much more complex field than that. There is a north and a south pole, but there is also another pole located, magnetic pole located on Jupiter just south of the equator, where a lot of the magnetic flux, a lot of the magnetic field is going into that very concentrated spot right there. So clearly, deep down inside Jupiter, it is much more complex than what we have going on the Earth. And this is one of the things that the Juno mission is trying to understand. Now, because of this strong magnetic field, Jupiter has strong aurora. This is a photograph of the aurora on Jupiter taken by the Hubble Space Telescope. Interestingly, the aurora on Jupiter, the particles that are trapped in the magnetic field line and are funneled to the north and south poles, those particles largely come from the moons around Jupiter. For example, this particular one right here comes from Jupiter's moon Io. And we can see that because if we look at where Io is and we trace the lines of Jupiter's magnetic field, we see that when we trace the lines of Jupiter's magnetic field, it ends up on that spot in the aurora of Jupiter. What we're seeing here are particles that are actually coming off the moon off Jupiter's moon Io, and those particles are getting trapped in the magnetic field. They're getting accelerated along the magnetic field, and then when they hit the atmosphere of Jupiter, they excite the atmosphere to glow, and it gives us that beautiful aurora on Jupiter. Now, A really interesting event on Jupiter happened back in 1993. In 1993, Eugene and Carolyn Shoemaker and another astronomer by the name of David Levy discovered an odd comet that had broken into about 24 pieces. It turns out the comet had had a particularly close pass to Jupiter, and during that close pass, it broke, as I said, into about 12 pieces. And then when they measured the orbit of this comet, they realized that it had had a very close encounter with Jupiter, and the tidal forces from Jupiter had torn it apart, but that those fragments entered an elliptical orbit around Jupiter, and that on July 16 to the 22nd of 1994, the fragments would collide with the planet itself just beyond the limb as seen from Earth. And so here are the cometary fragments that broke off of that comet. Here is an artist's rendition with a combined photograph of the cometary fragments and Jupiter itself. As these collided in July of 1994 with Jupiter, unfortunately, the site where they collided was not visible. It was just beyond the limb. But then the rapid rotation of Jupiter very quickly brought those collision sites into view. And in the infrared, we could see the heat from the collisions glowing for many days after the collisions. And surprisingly, in visible light, we could see dark spots in Jupiter's atmosphere that resulted from these collisions. The chemistry that caused these dark spots is still not well understood. It's not sure whether it was a chemical reaction between the comet and Jupiter's atmosphere. Are we just simply seeing dust from the comet suspended in Jupiter's atmosphere? But those little specks persisted on Jupiter for many, many months. They were visible and eventually gradually faded away from view. Since then, we have seen other objects hit Jupiter in the sense that we have seen dark spots like this on Jupiter that have appeared, and we believe that those were additional collisions that we have witnessed. I believe there were at least 2 additional objects have collided with Jupiter since 1994. Now, Jupiter has a set of rings. They're not nearly as spectacular as Saturn's rings. In fact, Jupiter's rings are impossible to see from with a small telescope on Earth. They were discovered by spacecraft that went out beyond Jupiter and looked back towards the sun. We can see these faint rings around Jupiter. As we will find out, all 4 of the Jovian planets, Jupiter, Saturn, Uranus, and Neptune, have ring systems. Saturn, of course, has the most complex and beautiful of the ring systems. Jupiter, Uranus, and Neptune have thin, faint rings. And now finally, let's move on to Jupiter's moons. Jupiter has well over 60 moons. We're only going to talk about 4 of them today, and those are Io, Europa, Ganymede, and Callisto, called the Galilean moons in honor of Galileo Galilei, who first observed them with his telescope. So the Io, Europa, Ganymede, and Callisto, they are some of the largest moons in the solar system. This white circle shows the size of our moon, which is one of the more significant moons in the solar system. So you can see that Ganymede and Callisto are actually bigger than our moon, and Io is almost exactly the same size as our moon. These are 4 fascinating bodies in their own right. Ganymede is the largest moon in the solar system. It's actually larger than the planet Mercury. If it weren't for the fact that it was orbiting Jupiter, we would probably call it a planet in its own right. But let's talk about each of them in detail. So here are some close-up images of them. So let's start with Io. Io is one of the most fascinating moons in the solar system. It turns out it is the most volcanically active body in the solar system. So I want you to take a look at this image for a second, and we're going to have our first Learning Catalytics question of the day. So I want you to go out to Learning Catalytics, and I want you to answer this question. Is the surface of Io young or old? So take a look at this image and try and decide, is the surface of Io young or old? So go out to Learning Catalytics, take about 10 seconds, and answer that question. So what do you think? Is the surface of Io young or old? Well, the answer to that is we need to count the number of craters that we can see. But here's the confusing thing about Io. What are all those spots that we see on the surface? Are these craters or are they something else? Well, it turns out in the case of Io, these are not actually craters on the surface. They are volcanoes. So on July 9th, 1979, as the Voyager 2 spacecraft flew by Io, It turned back to take a picture of the moon, and it saw extending above the limb of the moon two volcanic eruptions on the surface. And these two blue volcanic eruptions are each erupting about 100 kilometers or about 60 miles above the surface. Later, as the Voyager 2 images were analyzed, we saw other volcanic eruptions on the surface of Io. Io, it turns out, is the most volcanically active body in the solar system. And this is another spectacular image. This was taken by the New Horizons spacecraft as it was flying past Jupiter on its way out to Pluto. Many of the spacecraft that go to the outer solar system fly by Jupiter to get a gravitational boost, speed them up on their way to the outer solar system. And you can see here on on Io, a number of volcanic eruptions on the surface of Io. You can see one up here. You can see one over here. You can even see one here that is on the night side of Io, but the eruption is getting high enough that sunlight is catching it. This night side of Io is actually being lit up by the light from Jupiter itself. Io is the most volcanically active body in the solar system because of tidal forces from the planet Jupiter. Io is in an elliptical orbit around Jupiter, so at times it is closer to Jupiter, at times it is further away from Jupiter. It is also in a really interesting resonance with two of the other moons of Jupiter, with Europa and Ganymede. For every one time that Ganymede goes around Jupiter, Europa goes around twice, and Io goes around 4 times. And this exact resonance, where the moon's orbital periods are exact multiples of one another, means that they always come back to the same place, in the same orientation around Jupiter. In the case of Io, it's once every 4th orbit. In the case of Europa, it's every other orbit. And then in the case of Ganymede, it is every orbit. This orbital resonance is pulling and tugging on Io, as are the tidal forces from Jupiter. And they are essentially squeezing and releasing and squeezing and releasing and squeezing and releasing Io. And if you took a rubber ball in your hand and you just squeezed and released and squeezed and released and kept doing that over and over and over again, friction inside the ball would eventually heat the interior of the ball. And that's what's happened to Io. The tidal forces have heated the interior of Io such that there are molten layers under the surface, and they're erupting in giant volcanoes. In fact, the surface of Io is one of the youngest surfaces of any body in the solar system. There are hardly any impact craters on the surface of Io because the volcanoes quickly cover them over. So Io is an absolutely fascinating world. What we see here, by the way, the black spots that we see here on the surface, those are probably lakes of molten sulfur on the surface of Io. Molten sulfur takes on a very dark brown, almost black color like that. Much of the yellow colors that we see come from yellow and brown and red colors are coming from sulfur as well. So that is Io. Next out is Jupiter's moon Europa, the moon that I think is the most fascinating moon in the solar system. Europa, as you might remember from an earlier lecture, has an icy surface. The surface is made of water ice. So just taking a look at the surface of Europa, I want you to answer this question. Is the surface of Europa young or old? Taking a look at the surface of Europa, is it young or old? So go out to Learning Catalytics and answer that question. All right, so what do you think about Europa? Well, if you look carefully at Europa, it's hard with all of these dark stripes, but as we look at Europa, we can see impact craters on the surface. And so Europa does have some impact craters, so the surface is definitely older than Io, but it is not heavily cratered. It is not heavily cratered like the highlands of the Moon and Mars. And so the surface of Europa is, by geologic standards, fairly young. Now, what's fascinating about Europa's surface are these large cracks that we see on the surface of Europa. These large cracks have clearly been filled in by some material welling up underneath that is darker in color. And we have a number of pieces of good evidence that what is going on underneath the icy surface of Europa is a liquid water ocean. We have evidence from Europa's very weak magnetic field that there is a liquid water ocean. We also have this evidence from this cracking on the surface and that something has welled up and filled in those cracks. So there are multiple lines of evidence that deep underneath the ice on Europa, there is a liquid water ocean. And that makes Europa one of the only bodies in the solar system besides the Earth that has a significant liquid water ocean. Now, what's interesting about this is that Europa is also close enough to Jupiter that its rocky core may undergo some tidal heating, just like Io does. And that means there could very well be volcanoes at the bottom of this ocean on Europa. And that's important because that is where the first life on Earth formed. Initial life on Earth formed around volcanic vents at the bottoms of our oceans. Those initial life forms were chemosynthetic. They didn't rely on light from the sun, but instead relied on chemicals that came out of the volcanic vents for their power, for their energy. And it could be possible that there are volcanic vents at the bottom of the ocean on Europa. And that means that I believe that of all the moons in the solar system, there is Europa has the best chance that there could be life there. I don't know whether there is life or not, but I think it has the best chance of any planet. And so that's why I am so excited that we are building now, today, a mission to explore Europa called the Europa Clipper. The big question about the ice around Europa is whether it is thin or thick. And people tend to fall into two categories. There are the thick ice and the thin ice people. The thick ice model, the ice could be 10 to 20 kilometers thick, maybe even more than that. And with ice that thick, we could not imagine landing anything on the surface and drilling down through that ice to get to the liquid water ocean underneath. But there is a thin ice model where the ice is actually only a few kilometers thick up here. And if the ice is only a few kilometers thick, then the odds of some of this liquid water making it close to the surface are much greater. Now, there are plans in the long distance future to build a lander that would land on the surface of Europa. And the landing site would be carefully selected to be along one of these cracks where we may have material currently welling up from underneath today. But one of the things that the Europa Clipper is going to determine is using radar. It's going to try to determine whether Europa has a thin ice layer or a thick ice layer. There are chaotic terrains on the surface of Europa where it is clear that the water has gotten fairly close to the surface. The water might only be a few kilometers below the surface there. So these are areas where we believe that pockets of water have lifted up. Local spots of water have lifted up and the surface has broken apart and the water may be relatively close to the surface there. So the Europa Clipper is the next big mission to Jupiter. It is the first mission in NASA's Ocean Worlds exploration program. And the goal for the Europa Clipper is to launch sometime in the early 2020s, possibly the mid-2020s right now, go into an elliptical orbit around Jupiter and conduct 45 close flybys of Europa over a period of 2.5 years. It'll approach as close as 16 miles to the surface, and the projected cost of this mission is about $2.1 billion. So that's the Europa Clipper mission right there. There are many instruments that were selected back in 2015 to fly on board. I'm not going to go through all of them. There'll be an imaging system, of course, to take fantastic images of the surface with a resolution of 50 meters. But there is a radar for Europa assessment and sounding. So Reason is actually going to use radar to penetrate through the ice to determine how thick the ice is. There's a thermal imaging system, a spectrometer, a mapping spectrometer, all kinds of instruments that are going to tell us about the composition of the surface of Europa, look for organic materials down on the surface that might be welling up from underneath, and in particular study that ice layer to determine how thick it is. Next out in the solar system is Ganymede, Jupiter's large moon Ganymede. Ganymede is also an icy world like Europa and may have a liquid water ocean underneath. But in the case of Ganymede, that liquid water ocean is going to be buried under a much thicker layer of ice. Ganymede has far less tidal heating than Io and Europa, and so its ice crust will be much, much thicker. And it may be, though, that underneath that ice crust it also has a liquid water ocean, but buried much deeper. And then finally, out at the edge of Jupiter's system, we have Callisto, Io, Europa, Ganymede, Callisto. So take a look at the surface of Callisto here and answer this Learning Catalytics question. Is the surface of Callisto young or old? So go out to Learning Catalytics and take a few seconds to answer that question. All right, what did you find for Callisto? As you can see, looking at it, there are lots and lots of craters on the surface, and so Callisto clearly has a very old surface. It is like the other Jupiter's other large moons. It is primarily an icy, rocky moon. But Callisto is definitely has an old surface. So there has been no geologic activity that has reworked the surface of Callisto. Not only do we see thousands of individual impact craters on the surface, but there's even a giant impact basin on Callisto right there. With Ganymede, we do see some areas that have fewer impact craters than others. There is some evidence that there's been geologic reworking on Ganymede. And then, of course, lots of evidence that the surface of Europa and Io have been changed over time. But Callisto appears to have an ancient surface to it. So that is a very quick tour of Jupiter and its 4 major moons. In our next lecture, we will take a look at the planet Saturn and its large moon Titan. So join me in the next lecture for a close look at Titan and Saturn.